Okay, welcome back. This is going to be part 2 of Ampere's law. We, in the last video, went over the directionality and the math of infinite current carrying wires. This video will be concentrating on the geometry of the hoop and the geometry of the solenoid. Now, the geometry that is involving the hoop and the B field due to the hoop is a rather simple one. Unless you move anywhere else besides exactly in the center of the hoop. We're actually interested in only the exact center of the hoop because although there is a magnetic field everywhere in this inside this hoop, if you have a current running through your hoop, then and by through the hoop, I mean in the hoop itself, in the middle of the hoop. It has to be either this direction or the opposite direction. You should have a magnetic field that is formed everywhere inside the hoop, and as a matter of fact, outside the hoop there's a magnetic field as well. But it's not easy to calculate everywhere else. It is rather easy to calculate right exactly in the middle of the hoop. Now let's take a look at what it looks like. If we move our hoop over here to have plenty of space to draw our magnetic field, we can use our second right-hand rule, as we discussed in the last video, to grab the wire here in the front. The right side here I've listed as the front, and then the darker, smaller, sort of shadowed portion of it is in the back. If we grab the hoop here in the front, then our thumb has to go up, and you'll notice that the magnetic field that appears is going to be directed in this way, inside the hoop. And this magnetic field arrow goes directly through the middle of the hoop. It's true, no matter where you grab the hoop, that you would establish a magnetic field that is going here to the left. However, if you wanted to explore the way that it looks everywhere else, you would see that there is a somewhat warped field looks something rather like this. And I think this ought to look a little bit familiar to you. Here we have magnetic field going directly through the middle, and we would have magnetic field also going from right to left here at every other part of our hoop. So hopefully you recognize this as looking an awful lot like one of those bar magnets. And as a matter of fact, this is exactly how our bar magnets are created. So they're actually tiny little current loops all throughout a bar magnet. Now we can't really easily calculate the magnetic field everywhere else, but we can calculate it right here in the middle, and we can calculate it using this value, which I will put as a sub h for hoop. It's very similar to our previous equation. As a matter of fact, you might not even spot the difference. That's how similar it is. Mu naught times the current through our hoop, or around our hoop, divided by 2r. The difference between this and our infinite wire equation is that there's no pi in the denominator. This is available on your equation sheet as well as the other. What does r represent here? We do not want an r to represent some distance far away or some distance a little bit close to the wire. Instead, we want this to represent, and as a matter of fact, it's probably better to go ahead and write it as a capital R. We want this to represent the actual radius of the hoop itself. So this is then a value that is defined by the geometry of your hoop, the size of the hoop. A little bit stronger because you've actually wrapped your wire now into a circle, and you have contributing pieces from the entire thing. Not much more to the hoop geometry. It is interesting to note that this we sometimes refer to this as a dipole or a dipole moment. So you can actually create a hoop here, similar to the one that I just did, and put an arrow, and that represents then a current and a magnetic field. And this is given as the dipole moment, which is defined by the size of your hoop and the current that's flowing through it. Okay, so we'll move on to the solenoid because the solenoid is really important. Here's our third geometry. It's a little bit of a cartoon drawing here for this solenoid. So let me establish a better drawing. Now, in order to establish this better drawing, notice that what I've done is I've called back our old hoop, because you might want to consider what happens if I take a hoop and then I put another hoop next to it and another hoop next to it, and I just keep doing that. It wouldn't be necessarily a very efficient way running a single current through each of these hoops, but if I were to, instead of stacking hoops with individual currents, if I were to approximate hoops by allowing my hoop to continue around a second turn and a third turn and a fourth turn, and I just keep wrapping it into a coil, just like taking a wire and wrapping it around like a pencil, for instance, then what I've done is I've created a solenoid. Now, there are different names for solenoids. It's also called an electromagnet. It's also called an inductor or self-inductor. Or you can simply refer to it as a coil. So, and then of course solenoid. These have different connotations to them for the different uses of the solenoid. But the bottom line here is that you have hoops, and if you allow a current to flow this way through your hoop, it's going to go up in the front, and then it's going to go down in the back, and then it's going to go back up in the front, and then down in the back, and it's going to keep doing that, and then it's going to leave your solenoid out the other end. As it does this, if you were to imagine, if you take an imaginary hand and you grab one of these coils anywhere in here with your thumb pointed in the direction of the current, you would see that the magnetic field that forms in your solenoid is going to be similar to that of your hoop, and also similar to that of a bar magnet. Okay. Now, when it comes to solenoids, one thing that we're interested in is the inside of the solenoid. The outside turns out to be a little bit difficult to determine. But if you take a really long solenoid, this one's really short. If you take a really long solenoid, then let's take a peek inside that thing. So we're going to take a coil. Here we have all of our little hoops, right? And let's take a look inside the solenoid, and you could imagine it, really you could imagine it as like wrapping a wire around, let's say, like a cardboard tube, like a paper towel tube, and then if you were to investigate inside the cardboard tube, then the magnetic field that you would see, interestingly enough, it looks like a constant magnetic field. Now, in reality, we don't have infinitely long solenoids, and so Because of that, the strength of the magnetic field in the middle is the strongest, and they tend to die off a little bit toward the ends. But we're going to do all of our calculations as though we have at least a solenoid that is long enough in comparison to its diameter that we can approximate it as the simplest form of solenoid. When we do this, the simplest form of solenoid gives us a strength of the magnetic field inside a solenoid of, here's our friend mu naught again, and then we need some more features. Now you can imagine that if I pack these wires closely together, then I would strengthen the magnetic field. That would make sense, and it's definitely true. The number of wraps that I have per unit length is going to be really important here. So if I were to take the entire length of my solenoid and count all of the coils, that would represent this value. Or if I were to select just 1 centimeter and count all the coils within that centimeter, that would also be represented by that same fraction. There's only one more part to our equation, and that is, of course, the current. So if you up the current, or if you make a tighter density of coils, I call this also the coil density, then you will strengthen the magnetic field inside the solenoid. Now here's an interesting feature. Nowhere in this equation does it say anything about the radius of the solenoid. So as long as we have an effectively, at least small enough that we can consider this to be perfect, then in other words, it's longer, much longer than it is wide, then this equation holds everywhere in the solenoid. It is the same magnetic field strength right in the middle of the solenoid as it is right at the edge of the solenoid. It is a constant magnetic field everywhere inside. Now this is a powerful method for creating magnetic fields. You may remember from the previous video that the types of magnetic fields we were looking at were somewhere around 10 times 10 to the negative 4 times 10 to the negative 5 Tesla. Let's practice this now with another, a minor current. Let's make something small like 3 amps. So if we were to try our current through our solenoid is 3 amps, and how many coils do you think you could fit on every centimeter? You might be able to fit somewhere around, let's see, if we put for every 1 centimeter we were able to put, let's say, 100 wraps of wire. If we were able to do that by like stacking them on top of each other, then we would need to convert that, because remember, we prefer SI units, we would need to convert that to meters. So 100 in every centimeter would be 10,000 in every meter, right? So that's 10,000 per meter. Okay, and then of course mu naught is a constant, so we can just plug all of this in to calculate what we would expect out of such a reasonable solenoid. Okay, and if we run through that through our calculator, we get 0.0377 Tesla. Now, at a modest current and a reasonable coil density, we've still managed to get much larger than we had on the other two geometries by quite a bit, right? Remember, getting up to half a Tesla is quite difficult to do. If you want to do more than half a Tesla on these electromagnetic coils, then you're going to end up with high currents, very small wires, and you may remember from our Unit 2 that a very thin, tiny wire then has a higher resistance. So you need small wires to get a high coil density, and it tends to heat up too much, so we have to sort of water cool or some other way cool rapidly cool solenoids that you expect to get more than half of a Tesla out of. So these NMR, nuclear magnetic resonance coils, that some of you students will be using that go up past 1 Tesla tend to use either liquid nitrogen cooling, or they can use, in some cases, not just cooling from liquid nitrogen to keep it cool, but in some cases they actually supercool them because they use superconducting materials. So this is a sort of a physical limitation on these coils, but you can actually create your own electromagnetic coils and play around with them on refrigerator magnets and such, and without much concern. But if you really want a strong one, you're going to have to resort to some engineering. Okay, and that's it for our hoops and solenoids. In the next video, I'm actually going to introduce a consequence of Ampere's law with our Lorentz force, because we're going to have sort of a combination effect between the two.